In this example, we are going to take a look at this equation, and we're trying to determine whether the following functions are continuous at A, whatever these two values are. Justify each answer using continuity checklist. So as we kind of go through this, we're going to start off with the value that we're testing. 1, is it a domain issue? And then if it's not a domain issue, then does the limit exist at that value? And then we're going to compare that limit to what the actual Y value is. Right, that's what we're kind of going through to make sure that this thing either has a break or doesn't have a break, it's continuous or not continuous. So very first thing is, if I look at this, we have a domain issue and our X cannot equal 1. So instantly, we're not passing. It's going to be a break in the graph. It's not asking us for what kind of a break. It's not asking if it's a hole or an asymptote. It just wants to know, is it continuous or not? And so already our answer is no, that it is not continuous at X equals 1. And that is because f of 1 does not exist. Whether it's a hole or an asymptote, I don't know. We'd have to dig a little deeper into it, but that's not what it's asking for. Just, is it continuous? And if it is or is not, justify. There you go. All right, and on the second one, 2. 2 is not a domain issue. Well, that's good, right? So now we got to go a little bit further, and we're going to see if the limit exists. Well, the only possible break on this graph is going to be at 1. So it's going to be, the limit's going to exist. I just don't know what it is. So we're going to try to see what the limit is and see if it lines up with the Y value. All right, I have a feeling that we're going to be totally fine on this, but let's go through it. So if we're going to do the Y value, we're going to see what you get when you plug it in 2. And so we're going to do 3 times 2 squared plus 2x plus 1 divided by 2 minus 1. So we have a 4 times 3 is 12. 2 plus 4 plus 1 over 1. So 16, 17 over 1. We're going to get a value of 17. Great. Right, and then we'll do the limit. Now the limit, when we know that there is not a problem around that number, is as straightforward as plugging it in. So we're going to do 3 times 2 squared plus 2 times 2 plus 1 all over 2 minus 1, which we just did, and we know that we're getting a 17 out of that. Shouldn't box in. All right, so we're getting a 17 on the Y value, and we're getting a 17 on the limit. So is the graph continuous? Graph is continuous. Yes, continuous at X equals 2 because the limit as X approaches 2 of that function equals the Y value at that function. That is our answer and our justification. Right, and then we'll do one more. Okay, so we're looking at doing h of x. We have this piecewise function. It's broken up into this function at everything except 0. We can't plug 0 in because that makes that undefined, and so then we can't do sine of an undefined. But at 0, we're getting a Y value of 0. Great. So we'll start off with, is there a domain issue? No, because all of these values exist. All right, so I think I'm missing mine. A equals 0. All right, so 0 is our number that we're going to focus on. So is it a domain issue? No, we have a value for this, so it doesn't have to get kicked out. It's not a domain at all. So the first part of this is not a domain issue. Second part of this was going to be, does the limit exist? Okay, so for the limit to exist, we would need to do the limit as we approach 0, not equal to 0. That'll be the other part. So we need to do the limit. Put that over here. So if we're going to do the limit as X approaches 0 of X sine 1 over X, we got to figure out that limit. So to do that, this thing is always a problem. This is the sine curve that's oscillating, and the oscillation is kind of, we're not 100% sure. So this is a squeeze theorem kind of a problem. That if we take sine of 1 over x, just in general, a sine curve is going to range between a -1 and a 1. And if we multiply every single piece by an x, we'll get a negative x less than or equal to sine of 1 over x less than or equal to x. Okay, so here's why we're doing this. What is our limit? What is our limit as we are approaching 0 on this value? Right, so as we're getting infinitely close to 0, what's happening to a negative x? Well, it's approaching 0. And then what's happening on the other side as x approaches 0 on the positive x? It's also approaching 0. So if the limits of these two are approaching 0, then that means our limit of sine 1 over the whole thing. I dropped my x, sorry. There we go. Sorry, we should have been distributing an x to every single piece, and I forgot to distribute to that middle piece. So, all right, so if these are approaching 0, then our limit of this as x approaches 0 is going to be squeezed into a number in between, and that number in between is going to be 0 because it's going to equal it. So our overall limit on this is going to be approaching 0, right? So there's the limit part. And then, does the limit exist? Yes. And then does the limit equal the actual y value? Right, so if we do the actual y value, h of 0 is this line. So it equals 0. So our limit of h of x when x is approaching 0 is 0, which is equal to the y value when we plug in 0. So, is this continuous? Yes. Yes. Graph is continuous. It's continuous at x equals 0 because the limit of h of x as x approaches 0 is equal to the y value at 0. There's our answer, and there's our justification. Okay, and then we'll do a couple other properties and things like that in our next video.